Alright, so in this video, I'm gonna be explaining another important article with the title RAW-GNN, Random Walk Aggregation Based Graph Neural Network. So this HK paper in 2022 from Hong Kong. Graph convolution-based methods have been successfully applied to representation learning on homophily graphs where nodes with the same label or similar attributes tend to connect with one another. Due to the homophily assumption of graph convolutional networks, that these methods used they are not suitable for heterophilic graphs where nodes with different labels or dissimilar attributes tend to be adjacent. For example, a good example of heterophilic graphs is chameleon or squirrel dataset, chameleon dataset, because these Cora, Sightseer, PubMed has many nodes, more nodes than Sightseer, and Sightseer has more nodes than Cora, but all of these are somehow it has very high homophily. But these two datasets also archive. These datasets has high heterophily. That's why their performance is low. For example, Squirrel is around 49%, and this is a challenge. So the proposed approach integrates the random walk strategy with graph neural networks. The new method utilizes breadth-first random walk search to capture homophily information and depth-first search to collect heterophily information. It replaces the conventional neighborhoods with path-based neighborhoods and introduces a new path-based aggregator based on recurrent neural network. These designs make RAW-GNN suitable for both homophily and heterophily graphs. So there are several methods to deal with, have been proposed to deal with this homogeneity restriction. And these methods do not change fundamental aggregation mechanism. So we introduce a new aggregation mechanism, then proposes random walk aggregation. So it's a combination of random walk and GNN because it's a kind of aggregation again. Traditional neighborhood and random walk neighborhood. You see that the ego is very different from the random walk neighborhood. And so again, here we want to do node classification. We have aggregation and combination in most message passing neural networks, but the path-based neighborhood is new. The path-based neighborhood has already applied to heterogeneous graphs and knowledge graphs. Here we just modified our definition to make it suitable for heterophilic graphs. Formally, a path is the defined form of an ordered list, and K is the length of the path. A path-based neighbor of node I is denoted as P sub I, where the ending node in the list is V sub I. All path-based neighbor of node I collected by strategy S forms the path-based neighborhood. So the generalized edge homophily ratio, you can define it like this. When the similarity function is like this, if they are similar, their label is the same, then their similarity is 1. Then we sum over all such edges. So you get the total generalized homophily of the graph. And then, so we have some component like random walk generator. Consider a random walk that has traversed edge ETS, is now a node S, and is going to visit node R. It has already traversed node T, so we have the edge ETS. Now, what about ESR? We set the R normalized. So we say, what is the probability that the next node is R, given that S and T has already been seen. So DTR here, that is responsible for the definition of this movement, is just the length of shortest path between nodes S and R. So BFS collects information from immediate neighbors of the target node and can extract homophily information. Breadth first search. But depth first search tends to sequentially reach nodes at increasing distance from the source node, which can extract heterophily information. So given a path generator should learn the structural and semantic information of all nodes on P, not just the starting node and the ending target node, but also all the context nodes in between. Note that existing method that treat all neighboring nodes as an unordered set. Nevertheless, a path naturally comes with an order, which also preserves the ordered connection among the nodes of the graph. The objective of the path aggregator is to encode all the nodes on the path and consider the order of the nodes on the path to preserve more relational information among the connected nodes. The path aggregator for the Lth layer is defined using this 6, where H sub P is the Lth layer embedding vector for the path. So we can use any encoder that takes the order of elements into consideration, such as GRU, any variance of GRU, or RNN. Of course, GRU is a type of RNN. You can also use LSTM or any other types of recurrent neural network. And the attention-based intra-strategy combinator, this is when, after computing the path embeddings for every node, for strategy S, we need to combine them to strategy-specific node embeddings. We assume that given a certain sampling strategy, the generated path obey a corresponding distribution. Since all paths are sampled from the same distribution, it is reasonable to sum these paths to approximate the corresponding distribution. It is worth noting that the summation is different from combining node embeddings in GCNs because the pattern exhibited in a path cannot be well captured in a single node, beginning with summing node embeddings like typical GCNs weaken such path pattern. So alpha, this A sub P here is the learnable attention. And so the transpose, then we take the transpose of that. B sub P is the unnormalized importance weight of the path P. And now alpha is the path weighted normalized across all paths using just softmax. It is worth noting that we do not consider the embeddings of target node H sub I separately, again during the combination procedure. Since every path already contains H sub I, and to further stabilize the learning process, we adopt the standard multi-head attention, and specifically H attention heads are used and then their embeddings are concatenated. So you see the framework. First we have random walk generator, then we have RAW-GNN based path aggregator, then we have attention based intra-strategy combinator. But this one is very challenging because you have many paths, and the softmax, the summation is overall of the path. And finally the inner strategy combinator. So attention-based intra-strategy combinator receives path embeddings sampled by the same strategy and combines them into a strategy-specific embedding. Last, the inter-strategy combinator concatenates embeddings from different strategies to get the final embedding with minimal information mixing. So this is the inter-strategy combinator. After aggregating the path information within every strategy, we need to combine them using inter-strategy combination layer, since different strategies gather paths of different distribution. In order to combine embeddings from different strategies without mixing them, we use concatenation to combine embeddings from different strategies rather than summing them as done in GCN. And then we have the standard classifier, which is our cross entropy for node classification. Of course, it's a semi-supervised node classification. And these are the data sets, Cora, PubMed, CiteSeer that I talked about them. That I said PubMed has more nodes than CiteSeer, and CiteSeer has more nodes than Cora. That's why if you look at the performance, it says the same thing. Of course, PubMed, you see the distribution is much easier. That's why the performance is better than CiteSeer. But Cora is simpler than CiteSeer. So they compare different data sets and different methods, like even the GraphSage and GCN. If you compare them, you see that it's almost the same. For Cora, it's almost the same. For GraphSage and this method are almost the same. And then they said that the CiteSeer and for CiteSeer, the GraphSage and the RAW-GNN is just 1% different. Of course, this goes inside to the noise, so it's hard to decouple them to say which one is better. But you see that the GraphSage even has comparable results with the proposed method in this paper. So you see the visualization of Cora, because it's a node classification. You have different clusters, and it has high homophily. That's why all of them, it looks like a very good cluster. And you compare it for different models.